This is the second talk in the afternoon. No, the second session in the afternoon. And the first speaker is René Schwonnek from Universität Hannover. And he will talk about the activity of entropy uncertainty relations.
Yeah, thank you. Yeah, additivity of entropic uncertainty relations. So, this is on? Oh, yeah. Let me directly start by giving you the main statement of my talk, a little nice theorem on the additivity of entropic uncertainty relations. So this linear combination of two entropies, well, we could understand this as an uncertainty relation. So for a bipartite setting, XA, XB, and YA, YB are two pairs of measurements on distant locations, and well, we perform them on some common state rho AB. We look at such a linear combination, and well, one can ask, can I find a lower bound on such a combination? And well, this lower bound is what I call a linear uncertainty relation. You can also call it a Marsden-Uffing type bound. There are many names for it. And the main statement of additivity is, well, those relations are additive. They are minimized on product states. With this, you can, if you have a product state where you have the additivity of the entropy, and you can split such a minimization into two minimizations over each party. One where you only have to consider the A and the Y measure, XA and YA measurements, and the other minimization where you also only have to consider the B measurements. So this is additivity. And well, I give you more explanation on this in the following minutes. I will give you some motivation. How did I came up with such questions? Or why should we look at such questions? I will give you some interpretation, especially I will give you some interpretation for those coefficients which are maybe a little bit unusual in those relations. Well, and I will go to the proof a little bit. So main parts of the proof are really dragging down such a question on entropies to the level of PQ norms. And the main tool for doing this will be Golden-Thompson inequality. And well, when you're on the level of PQ norms, you can get a bunch of more results or more deeper insight into entropic uncertainty relations. For example, you can directly get a generalization of the Marsden-Uffing bound for such arbitrary weighted uncertainty relations. And well, on the level of PQ norms, this additivity question becomes a question of multiplicativity of PQ norms, which I will show you at the end of this talk. So, well, entropic uncertainty relations, short wrap up. Well, within the classification of, well, say, Busch-Rachte and Werner, this would be, entropic uncertainty relations would be a kind of a preparation uncertainty relation. This is, if we have two measurements, X and Y, well, we can take states, rho, and independent identical copy of the state, rho, and we can do, well, some measurements on this state with our X device or with our Y device. From those measurements, we'll get, well, some outcome statistics. You can get some probability distributions, Px, Qy, and you can look at the entropies of those distributions. And the big question here is, well, if we optimize over all states, can we find a trade-off between those outcome probabilities? So this is what will give you statements like, well, whenever the one entropy is small, the other has to be big, and vice versa. Yeah, so we are looking at trade-offs. And well, for this talk, let's get a little bit more specific. I'm only considering a projective setting where our measurements are given by some eigenstates, psi x, phi y. And well, we know how we can get probabilities out of this when we have a state rho. And well, when I speak about entropies, I always mean the Shannon entropy of those outcome distributions. Okay? And well, when we are in this projective setting, basically all information on such a problem is encoded within the unitary which links our bases. So we are not interested in measurement outcomes, only in labels, so we can encode everything in one unitary. And for thinking on uncertainty relations, let's have a short example. Think of a qubit, and you relate two bases by a Hadamard matrix. So two mutually unbiased bases for a qubit. And what you can do, you can think on such a diagram where you just, well, have your both entropies, and you pick some state, and for every state, you get a pair of entropies. And you can do this for many, many states, and well, you get a lot of such blue dots. So each blue dot corresponds to one state, and this is just a random sample of the whole state space. And in principle, you can think of doing this for the whole state space, which will give you some, well-defined set within such a diagram. And now uncertainty just means that you have some blank space here. Yeah, so you can't reach the 0, 0 point arbitrary well. And well, an uncertainty relation really corresponds to a good description of this blank space. So an optimal uncertainty relation really would be a description of this boundary here. And this is a geometrical picture, but you can always think of this as a representation for many algebraic things you can write down in order to describe the shape of such a region. Yeah, so this is an uncertainty relation, and you can do such diagrams. And actually, at the beginning of my PhD some years ago, I did this very, very, very often. So actually, the motivation was that Fabian Foer came up with some security proof where he used entropic uncertainty relations in order to judge security. And there really was the question, okay, can we improve such relations? How well are the known bounds on such relations in order to get more strong security statements? So we did a lot of those random samplings. Well, this is an example I already showed you, so for 1 qubit, but you can directly do this for 2 qubits or for 3 qubits. And well, what do you see? Well, basically the first thing you see is random sampling is a bad idea for this. So we, well, can do something more sophisticated. You can call it machine learning if you want. And you can get the shape of those corresponding uncertainty regions in this case. And well, what you can directly see, you see some structure. So you see those little, Reinhard likes to call it moon-like structures, where you can see that you can take the diagram corresponding to 1 qubit and really take this shape and plug it here, plug it here, plug it here. So you can build this whole diagram by this 1 qubit shape. And this is, well, a direct explanation for this is additivity. Or, saying more, if you only consider product states for those multi-qubit measurements, well, we know if we take some state for 1 qubit and tensor it with another state for 1 qubit and look for the corresponding entropy pair, well, those entropies will just add up as vector addition in those diagrams. And this is what I tried to plot here. So if we take this point here, or the state corresponding to this point, and just tensor it to it some other state from this diagram, well, you will get some point within this blue kite, whatever, blue shape. And, well, if you vary the state, you can really build up the whole green shape by tensor products of blue states. This is additivity, and the same works also for the yellow shape, or yellow uncertainty region. Yeah. So the big question is, well, can we prove such a statement? So this was numerically, and, well, we can do this for small dimensions. But, well, actually for general mutually unbiased spaces, we didn't achieve this yet. But, well, for this paper, this was okay. And if we consider entropic uncertainty relations, there's one big well-known bound, the so-called Marsden-Uffing bound, which gives you a lower bound on those relations, on those entropies, which gives you such a trade-off. And, well, this bound is additive. And more better, this bound is tight for mutually unbiased spaces. So the bad point is, well, this is a convex bound. So in terms of convex hulls, this Marsden-Uffing bound, and it's really not a big proof to see that this is additive, directly proves our desired statement of additivity of such diagrams for qubit measurements, well, mutually unbiased spaces. Well, and as I said, it's a convex bound. So the point is when you only have information or proven information on those, so the red line is the Marsden-Uffing bound, this linear bound. If you only have information on this bound, well, the basic thing you can say on such a diagram is, well, I have only those lines. And, well, if you further add the dimension of your systems, where you can conclude that the uncertainty regions are corresponding to those measurements, where I have to lie in this triangle. It's nice, and you know that you directly know that you can iterate this for, well, arbitrary tensor powers of qubit measurements. Yeah. However, and this is the question for my talk today, what happens if you consider general measurements x and y? First of all, we can see, okay, convex hulls of arbitrary sets are not always, or arbitrary uncertainty sets should not always be triangles. There could be actually more complicated shapes. And the other thing is, if we consider arbitrary measurements, the Marsden-Uffing bound is also not always tight. So we have to come up with a better bound for this. And just to give you some examples, this is again qubit, and theta corresponds to the angle between two measurement bases on a qubit. So on a qubit, you can basically parameterize all measurements by one angle up to a rotation, which doesn't matter for this entropy question. And we can see, well, it's really typical that we have convex uncertainty sets, and we can also see that we always have here some gap between the red line corresponds to the Maßen-Oefing bound, that we always have some gap between our set which we want to describe and the Maßen-Oefing bound. Yeah, so let's restrict to convex sets. And for convex sets, well, there's a nice way of describing those by linear relations, just by adding in such further weights lambda and mu. And the direct interpretation for those weights lambda and mu is, well, if I have some convex set and a linear bound on it, given in this form, well, those weights lambda and mu corresponds to the slope, or give you the slope of such a, well, tangenting hyperplane, such a line. And this lower uncertainty bound, well, corresponds to the length between this line to the origin. Okay, and again here additivity, the statement I showed you at the beginning, well, tells you that those linear bounds are additive, and this directly means for diagrams, uncertainty diagrams, that we can combine two uncertainty diagrams by the Minkowski sum, which is just, well, taking the point-wise or element-wise sum between two sets in order to get a new set. Yeah, so this is additivity in terms of geometrical representations, and there's also another way of looking at this. If you have such a linear weighted uncertainty relation, well, you can think about it in a sender-receiver setting. Sorry. Where we have one sender, let's call her Eve, and the receiver, let's call her Alice, and the sender prepares a state, and, well, Eve tosses a coin, and depending on the coin toss, she will either perform an X or a Y measurement, and let lambda and mu be the weights of this coin. So at the end, for every input state, in every single shot, well, Alice will get one of those 8 outcomes here. And, well, you can ask, okay, what is the uncertainty of the sender, Eve, on those outcomes? And this entropy is directly given by this linear entropy sum I showed you, up to a constant which only depends on the weights of the coins. Yeah? So the slow uncertainty bound directly bounds you from below the entropy or the minimal uncertainty Eve can get on the outcomes of Alice in such a setting, where you have one switch which changes your measurement devices. And, well, if we now go for this to a bipartite situation where we have additivity, well, we have now our two measurements, XA, XB, YA, YB. And, well, this can be directly passed by having two parties, Alice and Bob, which share one bit of classical communication in order to decide if they do, well, X-labeled or Y-labeled measurements. And here the only thing you really require for those measurements is that they share the same labels. So it shouldn't be that XB and XA should be the same measurements, only some identification of labels that Alice and Bob can share by this. And here the question again is, if Eve prepares a bipartite state, well, what is her uncertainty on the outcomes of such a joint measurement or joint measurement setting of Alice and Bob? And, well, there are, well, two obvious ways if you ask for a state which minimizes such a setting. So the one direction is, well, use product states which minimize those measurements locally. So Eve will choose a state which, well, gives her a good chance of guessing those outcomes and a good chance of getting those outcomes, but those outcomes between Alice and Bob's are independent. And the second strategy would be to use entanglement to produce some maximally entangled state which is somehow suitable for those measurements. And if Eve chooses such a strategy, well, she will have a lot of correlations between the outcomes of Alice and Bob, and if she wants to guess an outcome on such a measurement, well, she knows whenever she has a good guess for Alice's outcomes, she knows by correlation that she always will have a good guess for Bob's outcomes as well. So this reduces her uncertainty directly. However, what additivity tells you in such a setting, and this is maybe a little bit surprising, so usually entanglement helps, in such a setting, Eve will get no improvement by using entangled states. Yeah, so this is additivity, and it's clear if you have such a statement, you can directly, well, do this also for multi-partite measurements just by iterating the two-party statement to more parties. So if you add a further party, Charlie, and even more parties, well, you will have the same statement of additivity as well. And this would corresponds to such a communication setting where you now have, well, many parties all sharing one bit of communication in order to decide on their individual measurements. Okay. I see time is fine. So let me lose some words on the proof strategy or the proof. So 3 things I would like to show you. So first thing, okay, how can we connect such uncertainty bounds to PQ norms? And as I said, the tool will be the Golden-Thomson inequality. And if you have this, well, we can directly read off some generalizations of the Marsden-Uffing bound for such rates, lambda and mu. And, well, at the end of this talk, if we are on the level of PQ norms, this question of additivity translates into multiplicativity of PQ norms for unitary. And, well, let us directly start by rewriting the entropy in a, well, slightly different way as usual. So as a minimization of the self-information. So this expression minus log p prime is the self-information of some random variable x distributed by p with respect to a probability distribution p prime. And, well, we can get back the Shannon entropy by minimizing this over all possible unbiased probability distributions p prime. And maybe some more words to say on this. So if you're working a lot with uncertainty measures like variances or, well, min entropies and all things like this, they all can be written in a similar way like this. So from this slightly higher perspective, you can regard the self-information as a cost function or transport cost function, which gives you some notions of a distance between, well, an outcome of a measurement x and a probability distribution p prime. And so here taking the minimum would be asking for a, well, constant estimate which minimizes our transport cost between, well, x and p prime. And for example, if you're considering variances, you can use the squared Euclidean distance as a cost function, and you get directly, by minimization over all guesses for an unbiased outcome, the variance, and you can do the same for the discrete metric or for Gini coefficients. And so this is really a general ansatz. The nice thing on such an ansatz is, well, if we write this out for our quantum setting where we have a measurement x, where we get some expression which is linear in rho up to this minimization here. So we can use the linearity of the trace and just drag it out, and we can rewrite this entropy, and also variances and all those uncertainty measures can be written in a similar way as a minimization of a linear functional in rho. Yeah, so here a of x is just a substitution for this expression, which gives you a positive operator. So you minimize, well, a bunch of linear functionals, and by this you get your entropy, which is nice if you now look at such convex combinations, because we can directly plug in this rewriting, and, well, instead of having here something which depends on rho, well, in a very nonlinear way, we have something which is linear on rho, and, well, this linearity here gets directly transformed to a linearity in this expression. So this ay is just the similar substitution for our y observable, y measurement coming with a well, variation of a probability distribution q prime here. And if you have this and write this further out, well, there's one trick you can use in order to turn this minimum or this infimum over rho into a supremum. Well, if you have some function, you can apply some decreasing convex function, and, well, you can by this turn a minimum in a maximum. And, well, if you apply the inverse of this function afterwards, well, nothing really happens. Yeah, so we can do this to the spectrum of this operator pencil, and by this we get a function, well, where we have a supremum over rho, and this can be directly passed as a operator norm. And here you can already see, if we take this line to the next slide, this is some position where you can apply the Golden-Thomson inequality in order to get a lower bound for this. Or here we will get a lower bound if we have an upper bound here. And, well, if we do this, we can split it. And the nice thing is, if you write this out, well, short reminder, a of x has a logarithmic dependence on this p prime. If we write this out, well, we're losing all those logarithms and get some polynomials with respect to our p prime and q prime, over which we want to optimize later on. So this is very, very nice if you want to go on. I will skip all those steps. You can find it in my paper. So those are basically all equality signs. And if you go through all this, well, you end up with a statement that the uncertainty bound is lower bounded by the PQ norm. So this here is the PQ norm. You can think of this as the generalization of the operator norm between arbitrary Banach spaces. So here we would have Banach spaces given by the P norm and the Q norm. And short reminder, just for convenience, I call this P and Q norm. So this is not longer the P and the Q corresponding to probability distribution. Those are just parameters like in p norm and a q norm. Yeah, and by this we can get the uncertainty bound in terms of a pq norm. And well, those coefficients p and q's now depend on this initial parameter n, which we used within the estimate I showed you, or in order to turn the supremum into the infimum into a supremum. And they also depend on this weights lambda and mu, which, well, should come in somewhere on the right-hand side here. And the nice thing on this whole estimate is that if you do this for n to infinity, well, you again get an equality statement here. So this will turn into equality. So we really have the optimal bound if we do this for n going to infinity. And you can basically prove this by, well, it's very similar to the Trotter formula. So just this estimate here for n to infinity is basically doing nothing for bounded operators. Yeah, so if we have this, we can have a look at, well, those coefficients p and q. So how do they behave with respect to n and mu? And, well, for those of you who know the proof of the Marsden-Uffing bound, so within the Marsden-Uffing bound, something similar comes out at the end with p and q being Hölder conjugated pairs. This is 1 over p plus 1 over q is equal to 1. And here for arbitrary weights, we get that we get a similar statement for weighted uncertainty relations, but now with different p's and q's. And those are, well, I'll show you them in this diagram. And the thing is, if you can compute a PQ norm on some point in this diagram, you directly get a lower bound for the uncertainty sum for a linear uncertainty relation. And if you follow such a line, this is the same as dragging n to infinity, and you will get closer and closer to the optimal bound for this relation. So, well, I think this is kind of a nice result. And just for convenience, well, this right-hand side should really only correspond on the, or depend on the ratio between our weights lambda and mu. So those lines, well, even all correspond to a certain ratio. Yeah. What else to say? Well, when you have this, we have here the line corresponding to the Marsden-Uffing bound, and well, on the algebraic way, you can directly obtain the Marsden-Uffing bound from this relation by setting n equal to 2 and mu and lambda equal to 1. And for this case, as I mentioned, we will get our Hölder conjugated pairs for p and q. So p is equal to 1 and q is equal to infinity, and we get back the Marsden-Uffing bound as an instance of a PQ norm. And, well, you can even do more. As I said, whenever you can compute a PQ norm, you get a lower bound on an uncertainty relation for this attainable p's and q's. And you can think about this in a diagram of arbitrary p's and q's. So for this blue-green patch, those are the regions where the p's and q's that are attainable by positive lambda mu lie. So whenever we can compute a PQ norm within this set, we get a lower bound. And now you can ask, okay, can I compute PQ norms? And actually, this is a topic which has been investigated a lot in the past, and there are known results. So for this, well, triangle-shaped region, it is known that computing PQ norms is actually NP hard. And also on this, well, boundary curve, except the point 2, 2, it's also NP hard to compute PQ norms. So this does not help directly in order to get an uncertainty bound. However, there are points where we can compute PQ norms, namely those on those boundaries here. This point here, as I mentioned, 1 infinity corresponds to the Marsden-Uffing bound. Yeah, so we have the Marsden-Uffing bound as a easy lower bound on uncertainty relations because we can compute PQ norms in this case. And, well, we can also compute PQ norms on those regions, and this directly gives us a lower bound on uncertainty relations. Namely, if we go through the details, we can lower bound such a weighted sum of entropies by this expression, where this u vector x just corresponds to the x column of our unitary u. Yeah, and you can again see that at the end only the ratio of our weights lambda mu goes into this definition, and it's clear that this can be computed directly given that you have this unitary u. Okay, so we have by this a generalization of the Marsden-Uffing bound for this weighted situation, and, well, let me come to my last point. How do we get our additivity from this? how do we get additivity? Well, if we now go to a bipartite situation where we have some, well, local measurements, the corresponding unitary will have product form, something like this, and we are again interested on the lower bound of this form, and if we let this n let go to infinity, we will again get the optimal bound CAB in this case. And on the level of PQ norms, this additivity is directly translated into multiplicativity of the corresponding norm, so we have to show this for, well, matrices, not for quantum channels. And, well, there's a nice way of proving this. So let phi be some vector that lives in such a tensor product of, well, here about 10 Hilbert spaces, but in general you can think of, you only need the Banach space structure for this. And assume that you write down this state psi, well, in some product basis. So EA and EB are local bases. And by this you get such a phi ij. And for this phi ij you can define the following norm, which I think is some kind of a cross norm, where you basically first apply the p norm on the one tensor factor, and afterwards you apply the q norm or aq norm on the second tensor factor. If you think of this phi ij as a matrix, so just represent this as a bilinear form, this would correspond to just take the p norm row-wise, and afterwards take the q norm column-wise, and well, this will give you again a matrix norm. So if you look at a catalog of matrix norms, you will find this norm somewhere in here. And well, if we have this norm, and if we can prove the following properties, we can directly get the desired multiplicativity statement. So the first property we will need is really, if we have this q tensor q norm, and we evaluate it for, well, q equal to q, we get just back the usual q norm. So, well, if you, this is just saying that, well, if we have p equal to q, this vanishes, and we just evaluate the q norm on this whole tensor product here. And, well, the second property is when you have a unitary which only acts on one side and does nothing on the other side. And, well, you know that a PQ norm basically gives you an approximate or estimate for replacing this expression by this expression locally. And when we have that this also holds for, well, the situation where we don't touch one side, we will call this property 2, which we will need. And the third property which we will need is, well, this one here. If p is smaller than q and, well, we interchange the order in which we apply our p and our q norms by, well, here we first do the p norm, then the q norm. Here we flip our state and first do the q norm and then the p norm. And, well, if this gives us a clear direction, this is our third property. And from all those properties, we can directly get the multiplicativity proof as follows. So, well, we are interested in this quantity. And if we just write this tensor product out in 2 steps, well, we can directly replace this q norm by a q tensor q norm, do the first estimate on the right-hand side, get an estimate by the pq norm of the b unitary, then apply this flip quantity in order to flip p and q, and also the order in which we do ua and 1. And again, well, bound this from above by our PQ norm identity, property. And by this, you already have a proof for multiplicativity, yeah, which really only relies on those quantities. And I don't show you here how to prove those quantities for this particular norm I've chosen. Yeah. And, well, if you have this, you directly get multiplicativity of PQ norms. And by multiplicativity of PQ norms, well, we have the additivity of entropic uncertainty bounds. Okay. So, well, with this, I'm basically done already. Sorry. Was maybe a little bit quick. But I can say something on some open questions. So, one open question is, well, if you look at my proof, this proof really works only for projective measurements. So, one big question is, okay, what happens if we consider general POVMs? Second question is, well, such a proof for multiplicativity on the level of unitaries really works on this level of this very few properties I showed you. So what happens if we try to get this on the level of channels? And well, I know that this won't work for quantum channels, but I know that one can, or it should be possible to define similar cross norms for quantum channels. So maybe if you apply this technique to the level of quantum channels, you can maybe find a nice place where you can put the finger on the reason why additivity does not work for quantum channels, or quantum or multiplicativity does not work for PQ norms on quantum channels. And well, the biggest question, which I think is still open, what happens for this if you consider more measurements? So first thing to mention there, as far as I know, there's not a nice analog of the Marsden-Uffing bound for more than 2 measurements. I think this would be a nice thing to have. And well, you can ask for additivity of a situation where you have more than 2 measurements on one party, and actually this statement will fail. So it's easy to come up with a counterexample for additivity. I would guess that this is due to the fact that you will need more than 1 bit of information in this situation. And maybe one can do some kind of classical communication versus violation of additivity trade-off for the situation where you have more than 2 measurements. Yeah, and well, I think that's it. So, thank you. Yeah, I think there's still much time. Yeah.
Yeah, I was wondering if this theorem that you showed, or this technique that you showed, can be applied also to other entropy functions that are not the von Neumann one. For example, h-mean or h-mean smooth or something.
Yeah, good point. Good point. So I think there's one point. This rewriting of the entropy in terms of a transport cost function this here. I think this does, if you just consider René entropies, this does not directly work. If you go through the proof, well, if you have, oh, sorry.
No.
I want to show that. This here.
Okay.
Yeah. Actually, you can rewrite this expression in terms of René entropies, and you get additivity for a certain range of René entropies.
Yeah.
But additivity does not hold for all René entropies. So we have explicit counterexamples where additivity does not hold. And this is actually nice, so I don't have an answer to this yet. For which parameter range of René entropies does additivity hold or not? I don't know yet. So
okay, because if I understand correctly, if you prove additivity in this way, then you can use a Thomson rule,
yeah.
And then other. Yeah.
Yeah, maybe something to say on Golden-Thomson, or Golden-Thomson. It's clear that Golden-Thomson in this version I used it here only holds for 2 measurements, which nicely coincides with the fact that at the end the statement also holds only for 2 measurements.
Yeah, I know, but at the moment I'm fine with only 2.
Okay, okay, that's great. Yeah.
Have you looked at memory, adding memory to x and y and z?
Not yet, no. But actually, okay, this constant also. So you're thinking on this memory version of entropic constant.
What these guys done, right?
Yeah, I know. So I think this constant also appears there, right?
Yes, but then you
Yeah.
cannot use the PQ norm. You know, they're not. Then you have to use CD stuff, right?
Yeah. Not yet, but good idea. Good. Thank you.
Next questions?
Okay.
No, let's have the speaker finish.